Hello everyone, welcome to Peaks2Tails. Today we'll talk about Ito calculus. So this is typically how a stock price chart historically looks like. Now this can be decomposed into two parts. One is the deterministic part, which is the trend, and then the other part is the random or stochastic part, which is the fluctuation around the trend. Now when the prices are small, the fluctuations are generally small, and at higher price levels, there are bigger fluctuations. Question is how to model this process mathematically. So for simplicity, we'll start working in discrete time because it is easy to imagine, and then we'll slowly work our way to continuous time. So in discrete time, probably the simplest model is the simple symmetric random walk process. Now a walk is basically a series of steps. So each step in the random walk process has a chance to go up by +1 or -1 with equal probabilities. So this is one step. What is the expectation of a step? The expectation of this step is 0.5 times +1 plus 0.5 times -1, which is 0. So this step has a mean of 0. And the variance of this step is also straightforward, 0.5 times 1 minus 0 square plus 0.5 times -1 minus 0 square, which is 1. So this step has got a mean of 0 and variance of 1. What about the walk? Now walk is a sum of steps. Consider the walk has n steps. So the expectation of the walk is basically n times expectation of the step, which is again 0. And now this is true because expectation is a linear operator. Now the variance of the walk is n times variance of x, which is n times 1 equal to n, because the steps are IID, independent and identical. So there are no covariance. All right. Now, if we increase the n sufficiently, we know that central limit theorem tells us that the distribution of the sum would be a normal distribution. So the distribution of the walk, if n tends to infinity, would be normal with mean 0 and variance n. Let's look at an Excel animation for this process. So this is a simple symmetric random walk process. There is equal probability of going up and going down. Right now my location is at 0. Now the grid shows all possible paths that I can take in 4 steps. And the red path shows a sample path, which is random. All right. Now, because the sample path is random, my final location will have a distribution. It can reach any of the 5 terminal nodes, but the expectation or the average of all these possible paths will be 0. Okay, because there is equal probability of reaching each of those terminal nodes, right? It is symmetric. Now, since the future average is 0, which is equal to the starting position is also 0, we call that process a martingale. So martingale is basically a process where your future expectation is equal to the most recent value. All right. So if we move to, let's say, location 1 after step 1, for example, from this point onwards, if I take an average of the future values of my location, it will become 1, which is equal to the most recent value, which is 1. All right, so this property is called martingale. Now this would be true for all the intermediate steps as well, because the choice of 4 steps was really arbitrary. Now the martingale property says that the future average location or position or value of a process would be same as the most recent value. And here the simple symmetric random walk is a martingale because the expectation of each step is 0 because it is symmetric. Since the expectation of each step is 0, the expectation of all steps together is also 0, which means that in future I am expected to be exactly where I started from. So here I have plotted one sample path for the simple symmetric random walk, and you can see the distribution of the final position of the process. This is a sample distribution. So you can see the variance of the process increases with number of steps. And if you increase number of steps, the likelihood of observing extremes on both sides of 0 becomes more and more likely. That is because of the large variance. In other words, the further you look into the future, the more uncertain your position is. Now, since the variance scales with number of steps, with sufficient number of steps, you would expect the process to take more and more extreme values, which is desired because when you give a process some time to evolve, it takes more and more extreme values. For example, if you give time for a stock price to evolve, it can go up to any extent. So that is desired. The only problem is, right now, this process depends on number of steps. The variance depends on number of steps. But we want the variance to depend on the time, right? Steps is our way of thinking how the process evolves. But the process really evolves with time. So in order to make that adjustment, we have to scale down the up move and the down move factor by square root of delta t. And delta t is nothing but the total time divided by number of steps. Okay, we'll see in a bit why we made this choice. So this is called a scaled symmetric random walk process. Scaled because we have replaced the plus 1 minus 1 by square root of delta t and minus square root of delta t. Now, expectation of this process is 0. Again, it is symmetric. And the variance of the step is delta t. Now, this is the expectation and variance of the step. What is the expectation and variance of the walk? The expectation of the walk is still 0 because it is n times expectation of the step. And the variance of the walk is now capital T. So this is more desired. This is more usable in real life to model a stochastic process. And again, if we use central limit theorem, so basically if we just increase number of steps infinitely, then the distribution of the walk will approach a normal distribution with mean 0 and variance that scales with time, not steps. The process has to be step agnostic. It should depend only on time. Now, since the variance scales with number of steps, with sufficient number of steps, you would expect the process to take more and more extreme values, which is desired because when you give a process some time to evolve, it takes more and more extreme values. For example, if you give time for a stock price to evolve, it can go up to any extent. So that is desired. The only problem is, right now, this process depends on number of steps. The variance depends on number of steps. But we want the variance to depend on the time, right? Steps is our way of thinking how the process evolves. But the process really evolves with time. So in order to make that adjustment, we have to scale down the up move and the down move factor by square root of delta t. And delta t is nothing but the total time divided by number of steps. Okay, we'll see in a bit why we made this choice. So this is called a scaled symmetric random walk process. Scaled because we have replaced the plus 1 minus 1 by square root of delta t and minus square root of delta t. Now, expectation of this process is 0. Again, it is symmetric. And the variance of the step is delta t. Now, this is the expectation and variance of the step. What is the expectation and variance of the walk? The expectation of the walk is still 0 because it is n times expectation of the step. And the variance of the walk is now capital T. So this is more desired. This is more usable in real life to model a stochastic process. And again, if we use central limit theorem, so basically if we just increase number of steps infinitely, then the distribution of the walk will approach a normal distribution with mean 0 and variance that scales with time, not steps. The process has to be step agnostic. It should depend only on time. So let's see an Excel animation for this. So in scale symmetric random walk process, the idea is to keep the time horizon fixed, that is from 0 to 1, and change the number of steps, but also change the up move factor and the down move factor. So basically we scale the up move factor and down move factor in such a way that the variance at time t equal to 1 remains constant, which is equal to t in our case, and since t is 1, our variance will remain as 1. So keep an eye on the sample variance here. Right now there is only one step, right? I'm going to increase the number of steps, but accordingly I'll scale down these two factors. These are square root of delta t and minus square root of delta t. And delta t is t divided by n. As you can see, the variance remains constant, close to 1. So as I'm increasing the number of steps, the up move and down move factor gets scaled down, and the final variance of the process at t equal to 1 remains 1. Also, the scale symmetric random walk process takes us one step closer to the continuous time models because we are able to indefinitely increase the number of steps, making it look more and more continuous. But at the same time, we are ensuring that the final variance is not steps dependent, but it is time dependent. And that is the desired feature of our process. Now this distribution, which is normal and has a mean of 0 and variance t, has a special name in continuous time. It is called as the standard Brownian motion, denoted as bt, which is normally distributed with mean 0 and variance t. Now standard Brownian motion becomes the fundamental currency of modeling randomness in continuous time. Now, if this is the desired distribution of a process, which is normal with mean 0 and variance that scales with time, what happens in a given step or a small time interval dt? We don't have to go back to scale symmetric random walk again because that is in discrete. Can we think of a continuous process which, when aggregated, will become this process? Well, since this is a normal distribution, we know that when we aggregate normal distributions, the resultant is another normal distribution. So what happens in that small time interval from a given time t to time t plus dt is called the increment of the Brownian motion, which is also normal with mean 0 and variance dt. When we add a whole lot of these increments together, the mean remains 0 and the variance simply gets added. So when you add the dt term from time 0 to capital T, it becomes capital T. So on the left hand side, we have the standard Brownian motion process. On the right hand side, we have dbt, which is the increment of the standard Brownian motion. Visually, it looks something like this. Let's look at an Excel animation for this. In this plot, I have various sample paths of standard Brownian motion, and then also the distribution of the Brownian motion at time t. I'm going to increase time slowly. Right now it's at 0.01, so you're seeing a very concentrated distribution around 0. I'll increase the time slowly, and you'll see that the distribution will diffuse and the variance will increase with time, right? Because variance is equal to time. So as time increases, the variance will increase, and you'll see higher and higher dispersion with time. And this is similar to the idea of scale symmetric Brownian motion. Only difference is that was in discrete, where only 2 states were possible. Here it is all continuous, so all states are possible. Let's look at some of the definitions and properties of Brownian motion. B0 is equal to 0. So at time t equal to 0, the Brownian motion is equal to 0. This is just convention. Brownian motion has independent and stationary Gaussian increments. This is probably the most important property of Brownian motion. Each increment is independent and stationary and Gaussian. Brownian motion is continuous everywhere, but differentiable nowhere. We'll come back to this point after some time. Covariance of the Brownian motion between 2 different time points, s and t, is given by minimum of s comma t. The Brownian motion is Markov as well as Martingale. Then we have the scaling property. So this term is also standard Brownian motion. And time inversion property. So this is also a standard Brownian motion. So next, let's look at each of these properties in a little bit more detail. So the first one is independent stationary Gaussian increments. So the plot shows 2 different increments at 2 different time intervals. One is from s to t, the other one is from s1 to t1. So the theorem says that the increments are independent, meaning if the increments are in non-overlapping time zones, then they are independent. So the covariance between the increments on time intervals which are separate will be 0. Next property is that the increments are Gaussian. So if you look at the expression, the increments are normally distributed, hence they are Gaussian. Third point is increments are stationary. Stationary in the sense is that the distribution has a 0 mean, which is same everywhere, and the variance does not have explicit time dependence. It only depends on the time difference between the reference points. Hence it is stationary. Next, let's look at this property. The Brownian motion is continuous everywhere, but differentiable nowhere. So we know that dBt is normally distributed with mean 0 and variance dt, which can also be written as z times square root of dt, where z is the standard normal distribution. Now dB by dt is, we can write by replacing bt with z square root of dt, and that has an order of 1 by square root of dt, because z is a finite number, which is random but finite. So we get an order of 1 by square root of dt. Now that dt tends to 0, this whole thing tends to infinite. So slope is undefined. So even if Brownian motion is continuous everywhere, it is not differentiable. So dB by dt is meaningless. In calculus, in stochastic calculus, we do not write dB by dt, but we write differentials, because dB is meaningful. dB is a random draw from normal distribution with mean 0 and variance dt, but dB by dt will be meaningless. Let's look at an Excel animation, a visual that shows how Brownian motion is continuous everywhere but not differentiable anywhere. In order to show you the non-differentiability aspect of the Brownian motion, I have plotted two curves on the same page. The orange one is a smooth curve given by 10 sine 0.1 t, which is differentiable everywhere, and then the blue curve, which is the Brownian motion. Now, the idea is if we zoom this plot sufficiently, the smooth curve looks like a straight line. And that's how the slope of a curve is defined, because it has to approach a straight line at a given point. But the Brownian motion, which is the blue one, does not become smooth, no matter how much you zoom. It remains as squiggly and jagged as it was before. So let's look at the next property. The next property is covariance between Bt and Bs is minimum of T and S. So let's assume that S is less than T without the loss of generality. Covariance between Bs and Bt can be written as covariance between Bs, and then we write Bt in this fashion, which is Bs plus the increment between S to T. So the increment is Bt minus Bs. We'll separate this term into two terms. One is covariance between Bs and Bs, and the other is covariance between Bs and the increment, which is after S. All right. The second term will be 0, because what happens after S has nothing to do with what happened before S. So between Bs and Bt minus Bs, the covariance would be 0 because the increment would be independent. And the first term is nothing but the variance of Bs. And variance of Bs is nothing but S from the distribution. So we are getting S. Now we assumed S less than T, so we got the answer S. So we can say in general that the covariance between Bt and Bs is a minimum of S and T. Okay, the next property is that Brownian motion is Markov and Martingale. This is probably one of the most important properties. So we'll use the property of independent increments. We know that the increment is Gaussian with mean 0 and variance, which is the time lag. We can write Bt as Bs plus z times square root of t minus s. So z is standard normal. Now the distribution of Bt given Bs. So we look at the expression Bt equal to Bs plus z times square root of t minus s. So the distribution of Bt given Bs only depends on Bs. It does not depend on the past values. Okay, so the distribution of Bt only depends on Bs, which is the last known value. And that is called Markov. So if we look at the plot here, assume that the Brownian motion has taken some path till S, and we know Bs is the value of the Brownian motion at time S. What happens in future time t is obviously random, and it will have a distribution, but the distribution Bt given Bs will be normal with mean Bs, right? Because the increment Vt minus Bs has no mean. Mean is 0 for the increment. So the mean of Bt will be exactly what it was before. The last known value was Bs, hence the mean will also be Bs. And the variance is the same as the variance of the increment, which is t minus s. So we see that the distribution of Bt given Bs depends only on Bs and not on the entire history or the past values. So this is called Markov, and this is also memoryless. It has no memory. It does not matter how you got to Bs. All that matters is where you are at today or at time S, and that only determines the future distribution. Similarly, we also know that this Markov property is enforced because of independent increments. So whenever we have a stochastic process that has independent increments, that imply Markov. Reverse is not always true, but independent increments will imply Markov property. Also, we can see that the future distribution of Bt given Bs has a mean equal to Bs. Whenever future distribution have a mean equal to the last known value, we call that as Martingale. So Brownian motion is both Markov and Martingale. And related to the increments, so independent increments imply Markov, and increments which have a zero mean will imply Martingale. Because if the increments do not have any value on an average, then you don't expect the process to grow, because the increment has a zero expectation. So zero expectation of increments will imply a Martingale process. Let's look at the next property. So the scaling property, this is pretty straightforward. So if you look at this expression, 1 by square root of c times bct, so bct means the Brownian motion at time ct, all right, and that has been scaled down by a scaling factor 1 by square root of c. The theorem is saying that this quantity is also a standard Brownian motion. So we'll take the expectation, and 1 by square root of c will come out. It is a scalar, and then expectation of bct is 0, so the mean is 0. Let's look at the variance. Similar idea, the constant 1 by square root of c will come out as square, so 1 by c, and the variance of bct. Now we know that the variance of bct would be ct, so this is equal to t, all right, and scaling a normal distribution results in another normal distribution. So the overall distribution of this quantity is normal with mean 0, variance t, hence this is standard Brownian motion. Next, let's look at the time inversion property. It's the same argument, but it's a different quantity. So t times Brownian motion at time 1 by t. This is also standard Brownian motion. We follow the same process. Expectation would be 0, and the variance is coming out as t, and it will be normal. So this quantity is also standard Brownian motion. Let's look at the next property. Next property is quadratic variation. So the quadratic variation property is the most crucial property of Brownian motion. Consider a time interval between 0 to t and a small time interval dt at a given time t. Now in that small time interval, the quadratic variation is defined as square of the increment, that is dv square. Now what is the expectation and variance of db square? We know the expectation and variance of db, but what's the expectation and variance of dv square? So the expectation is expectation of dv square is the expectation of a normal variate that has a mean 0, variance dt. We can replace that normal variate as z square root of dt, and then whole square would become expectation of dt times z square. Dt is a scalar, it will come out, and then we have expectation of z square, which is 1. So we get dt. Expectation of dv square is dt. Let's look at the variance. The variance of dv square is variance of dt times z square. Dt comes out as dt square. Then we are left with variance of z square. Now variance of z square is 2, because if z is standard normal, then z square is chi-square distribution, and this, since we have only one standard normal, it will have a chi-square distribution with degree of freedom 1, and the variance of a chi-square distributed variable with degree of freedom 1 is 2. So we have 2 dt square. But looking at the time interval dt, if the expectation is equal to dt, the variance is way smaller than dt. It is 2 times dt square. So that approaches to 0 in a small time interval tt. So we have a quantity which is pretty interesting. This quantity dv square has an expectation of dt but the variance of almost 0. So it behaves like a deterministic quantity. So in summary, we have dB that is normally distributed with mean 0, variance dt, but dB square is normal with mean dt but variance 0, as if it is purely deterministic. So in whole of Ito calculus, you will see the term dB square being replaced by dt. Now, Brownian motion as is not suitable for modeling because it has no parameters. So it is a good source of modeling randomness, but we need to tweak it to suit our purpose. So Brownian motion has a mean of 0 and variance of t. What if we need a different variance? Then we need a parameter that we can play with so that we can have a desired variance. Similarly, if we want a non-zero mean or a drift or a trend, we need to add something to the Brownian motion process. So this particular process is called arithmetic Brownian motion. It is one level of enrichment on Brownian motion. So we have a different variance and we have a different mean. Sigma bt is the stochastic part and mu t is the deterministic trend part. So we have chosen two additional parameters to have a desired variance and desired drift. If you differentiate this process with respect to t, we get this expression, but this expression is meaningless because dv by dt is meaningless. So in stochastic calculus world, we do not write derivatives, we write differentials. So instead we would write dyt is equal to mu dt plus sigma dbt. So this is an equation involving differentials, not derivatives. And this is called a stochastic differential equation. The original process yt equal to mu t plus sigma bt is the process or the solution, you might think like that. And this equation dyt is equal to mu dt plus sigma dbt is the stochastic differential equation. And as we mentioned, mu dt is deterministic and deterministic part of the equation, and sigma dbt is the stochastic part or the random part of the equation. So let's look at an Excel animation for this arithmetic Brownian motion process. Now this is arithmetic Brownian motion. So we have two parameters, mu and sigma. With mu we control the drift, with sigma we control the volatility. So right now it should be upward drifting. You can see the red path, which is the trend. Let's go back. Similarly, we can have a negative trend. Let me try -1. So the trend actually shows where the mean is of the distribution. Let's go back. Set this as 1. Let's increase the sigma a little bit so you can see higher dispersion. So it diffuses faster. Similarly, you can have a lower sigma. Right, so this visual was to give you an idea of how the distribution and the path looks like with various choices of the parameters, mu and sigma. Now the arithmetic Brownian motion process is not suitable for stock price modeling. because this process can become zero. And we know that stock prices cannot become zero. It can become zero because we have this term bt, which is a normal random. And normal randoms can take values from minus infinity to plus infinity. So there is nothing restricting this process to go down below zero. So this process is not suitable for stock price modeling. One thing we can do is to put the whole thing into exponent, so that even if this yt, the mu t plus sigma bt part becomes minus infinity, still in the worst case we'll have zero, because e to the power anything has a floor of zero. It cannot become negative. So when we put the whole thing into exponential, it is called a geometric Brownian motion. What is the SDE, or stochastic differential equation, of the GBM? Now, ordinarily you would expect, since we have a e to the power something on the right hand side, we'll take log and differentiate. So we would expect log y is equal to mu t plus sigma bt, and then if we differentiate both sides, we'll get dy by y is equal to mu dt plus sigma dvt. Right? That is from the ordinary rules of calculus. Turns out it is not so simple in stochastic calculus. The true SDE for this process is dy by dt equal to mu plus half sigma square times dt plus sigma dvt. So there is a correction term of half sigma square. Now how does it come into the picture? Welcome to the stochastic calculus. We'll look at Ito calculus, Ito lemma, and other theorems, which will help us move seamlessly back and forth between the process and SDE. Before we go there, let's look at an Excel animation for the geometric Brownian motion. So this plot is to show you the various sample paths of a geometric Brownian motion process and the terminal distribution of the process. Now this is a log normal diffusion process because it is geometric Brownian motion. Also, you can see that the trend, which actually shows the location of the mean of the distribution, is not linear, it is exponential. So we have talked about SDE, which is a stochastic differential equation. Generally, it will be of this form. So there will be a drift term and there will be a volatility term. The drift term can be a function of the process level itself and time. Volatility can be a function of the process level, which is yt, and time. The drift is responsible for the mean of the distribution, and the volatility is responsible for the dispersion. So from SDE, we can go to the solution or the process using Ito integral. Now, how is this Ito integral special? Because now we are dealing with the term dbt. This is a random increment. It is not deterministic. So there exists a special machinery to navigate or calculate integrations with respect to Brownian motion increments. So that is called Ito integral. So from SDE, we can go to process using Ito integral. And then from process, we can find its SDE using either Ito's lemma or Taylor series. Personally, I prefer Taylor series because it is pretty mechanical. But if you want to remember Ito's lemma, there are 3-4 variations depending on whether it is a function of time alone, or function of time and level, or constant. So if you use Taylor series, you'll always get the SDE without remembering a whole lot of different variations. So let's look at Ito integrals. Now, before we jump into some examples of Ito integral, it's always helpful to remember this diagram. So when we will work with Ito integrals, it is always the go-to strategy is to convert the Ito integral into a discrete sum. Integral is, after all, a sum. And if we look at the whole integral as a discrete sum, we we should always have this picture in the head. So at each point we are looking at Brownian increments dB, which are independent, Gaussian, stationary. All right, at every single point there is this Brownian increment dB, which is a normal random distributed variable with mean 0 and variance dt. So this is the picture for increments, and this picture below is the actual Brownian motion process, which evolves over time, and this has a dispersion that increases with time. So the variance will scale with time, and this is nothing but just adding up the increments. All right, so this picture is really handy when we work with E2 integrals. All right, let's look at some examples. The first one is pretty simple. So it is integration with respect to dbs. There is no integrand, or you can say the integrand is 1. So this is pretty straightforward. This is just bt minus b0, and that is equal to bt because b0 is 0 by convention. And bt is nothing but a normal distribution with mean 0 and variance t. So this is a little bit peculiar compared to what we are used to seeing in ordinary integrations, because the output of this integration is a random variable. Next example, a constant times dbs. So that is k times bt. It's pretty straightforward. The constant comes out. No worries. So this would be a normal distribution with mean 0, variance k square t. Let's look at a little bit more complicated example. So consider the integrand is a time-dependent function, f of s, which depends on time. This is a disjoint function. The way it is defined is between 0 to 1. When time is between 0 to 1, the value of the function is 1. When the time is greater than 1, the value of the function is 2. So what we do is definitely we'll break down the integration to suit these intervals. So from 0 to 1, and then from 1 to 2. Between 0 to 1, the function is 1. Between 1 to 2, the function is 2. These are the scalars. They come out, and we get this. Now this expression is nothing but sum of two Gaussian increments. The first one is normally distributed with mean 0, variance 1, because the time lag is 1 between 0 to 1. The second one is 2 times, again, a normal distribution with mean 0, variance 1, but the 2 can go inside and become 4. So we are looking at sum of two normal distributions. So the resultant is another normal distribution with mean 0 and variance 5. Next, let's look at a little bit more complicated example. So instead of a disjoint function, we actually have some function which is time dependent. In general, we have any function f of s which is time dependent. How do we integrate? So the idea is to start imagining this integral as a discrete sum. So we'll break down the whole interval 0 to t in small intervals. Each interval is dt. All right. Now we look at this integration as a sum. So f evaluated at each of those points I, and then the small increment dbi, and then we take a sum of these products at each different point. So this is looks like a weighted average of Brownian increments, and the weights are the function values at each point. All right. Now since this is a linear combination of normal randoms, because dbi, remember, is always a normal is a draw from a normal distribution 0 dt, right? So this is a linear combination of normal randoms. So the output will be a normal distribution. Call this as I. We already know that this will be a normal distribution. What is the expectation of this integral? So expectation would be, since fi is a scalar, it's not really random. The expectation is with respect to the random component, which is dbi. And we know that the expectation of every increment is 0, right? So this entire expectation of this integral is a big 0. What is the variance? The variance is also easy to calculate, because in all these intervals, since these intervals are separate and not overlapping, the increments are independent. If they are independent, the variance of a sum is the sum of individual variances. There is no covariance term. So we can write, so f square fi would come out as f square I, then variance of dbi, and we know that the variance of any increment anywhere dbi would be dt, stationary, right? So we get f square I dt. Now this expression, sum of f square I dt, is nothing but the integration of f square s, the function, ds 0 to t. So if you look on the left hand side, this is just the way we calculate the integration as an area numerically, right? That is that expression. So we get this as integration of f square s ds 0 to t. Now all together, since we know that the output is normal distribution and we have the mean, we have the variance, we can write the integral is normally distributed with mean 0 and variance 0 to t integral of f square s ds. What if the integrand itself is a Brownian motion? So this one is actually tricky. It is not straightforward. So we will come back to this one in an indirect way. So let's look at our first example of Ito lemma or Taylor series. Consider this process y equal to bt square. The change in y dy is given by the Taylor series expansion. We have the first order term, which is del y by del b times db, plus the second order term, which is half times second order derivative times db square. Now from the results, we know that we can replace db square with dt. So this is something that we'll be continuously doing in Ito calculus. And we can also calculate the first order and second order derivative of y with respect to b. So first order derivative is 2b, second order derivative is 2. So we replace those two in the equation. And then we integrate both sides. We get the left hand side will become y is bt square, and on the right hand side we have 2 times integral of b db 0 to t, and then integration of dt is simply t. So we get the integration of b db 0 to t as half of bt square minus t. And this is what we wanted to calculate previously. We got this in an indirect fashion using Taylor series. So far, all the Ito integrals we have seen are normally distributed with mean 0 and some variance. Since all of those have 0 mean, we can say that Ito integrals are martingales. They have no expectation. So on an average, you would not expect them to grow or shrink. There is no drift. So in order to show that a process is a martingale, if we have the SDE of that process, then the drift term has to be 0, because the drift term is responsible for the trend or the mean of the distribution. If the drift term is 0, then the process will have a 0 mean. So that is what is written here. A process to be a martingale, the drift term of the SDE has to be 0. Even this term that we just saw is an Ito integral, and it is also a martingale. One way to show this is Martingale is that if we look at the SDE of the process is, if you look on the left hand side, it is just BdB accumulated over time, right? There is only dB term, there is no dt term. So it is 0 times dt plus BdB, that's the SDE. Since there is no drift, it is a Martingale. If it is a Martingale, we can say that the expectation of bt square has to be equal to t. Only then the expectation of the whole process, which is bt square minus t, will be 0. So we must have expectation of bt square equal to t for this process to be Martingale, which we know is true because if we look at expectation of bt square, it is expectation of t z square, right? Bt is z square root of t. Now t comes out, we have expectation of z square. Expectation of z square is 1, so we get t. So in order to show a process is a Martingale, the definition is future expectation has to be last known value. In this case, it will be 0, right? The other way to show this would be if we have access to the SDE of the process, then the drift term has to be 0. So next, let's look at exponential martingale. Now this process y equal to e to the power mu t plus sigma bt will be called as exponential martingale if it has no drift. So basically it's the same martingale, but it has a special name because it is e to the power something. So we call it exponential martingale. Now one way to show this would be if we can derive its stochastic differential equation and set the drift as 0, then we can say this is a martingale. So let's do that. Now we can see that y is a function of both time and the Brownian motion. So there are two variables. It's a bivariate function. For Taylor series expansion, we need to calculate the first order and second order derivatives with respect to each of these variables. Also probably the mixed derivative as well to start with. So let's calculate those. First order derivative with respect to time, second order derivative with respect to time, first order derivative with respect to Brownian motion, second order derivative with respect to Brownian motion, and then the mixed derivative. Now we use the Taylor series expansion. We have the first order terms, two first order terms, two second order terms, and one mixed derivative, which is also second order. Now question is, which terms do I keep? Which terms are significant in the time interval dt? So we look at the order of all these changes. So the ones in green are the ones I keep. The first one is dt, I'll keep that. The second one, dB, is z square root of dt. So square root of dt is even more significant, I'll keep it. The third term has an order of dt square, I'll ignore it. The fourth term is the key component, right? dB square, which we know is dt, so I'll keep that. And then the last term will have an order of dt to the power 3 by 2. So I will ignore that. So collecting these significant terms, I get this. Now for y to be a martingale, it has to have 0 drift. So I put the drift as 0, then I get a condition between mu and sigma. So mu has to be minus half sigma square. So this process yt equal to e to the power minus half sigma square t. So I just replace mu with minus half sigma square. Y equal to e to the power minus half sigma square t plus sigma bt will be an exponential martingale because it will have a 0 drift. So let's look at an Excel animation for this exponential martingale. This is the plot of an exponential martingale. It is a geometric Brownian motion still, so it will still have a log normal diffusion, but the mean of the diffusion remains constant with time. Hence it is a martingale. There is no drift. So let's look at the next property. The next property is Ito isometry. It is one of the very important properties. So we looked at this particular integral. It was a simple case where the function or the integrand was a deterministic function of time. Ito isometry tells us that the expectation of square of an Ito integral can be written as integration of expectation of the square of that integrand with respect to time. And this Ito isometry property comes in handy when we want to calculate the variance of various Ito integrals. So we'll see an example. The variance of integration of BdB is, now we already have calculated the integral BdB, so we'll just replace that. So this is bt square minus t by 2, then 1 by 2 comes outside as 1 by 4, and the term t does not really contribute to the variance, so it is just bt square. Now the variance of bt square, we can always replace bt with z square root of t. Square of that would be z square t. Again, variance of that, so t square would come out, and we are left with variance of z square. Now variance of z square is 2 from chi-square distribution. So we get this expression, and this is t square by 2. Now let's use Ito isometry to get to the same result. So we start with the variance of this quantity. Now Ito integrals are martingales, which we saw, and this quantity will also have a mean of 0 because it is martingale. So if it has a mean of 0, we can write variance as expectation of square of this quantity because there is no mean. Now immediately we can use Ito isometry to convert this integral to this form. Now we know expectation of bs square is s. So we write this as s ds, and then we integrate and put the limits, we get t square by 2. The next important result is Ito product rule. So if we have two SDEs, dx1 and dx2, given by mu1 dt plus sigma 1 dv1 and mu2 dt plus sigma 2 dv2, and assume there is some correlation between dv1 and dv2, the correlation is rho, and then the change in x1 times x2, which is the product, d of x1 x2, typically in ordinary rules of calculus, we retain the first two terms, which is x1 dx2 plus x2 dx1, and we ignore the third term, which is pretty negligible compared to the other two terms. Geometrically, x1 and x2, let them represent a rectangle, and x1 times x2 is the area of the rectangle. Then d of x1 times x2 is nothing but the change in area of the rectangle, which is attributed to both change in x and x1 and change in x2. And the third term is this tiny area on the top right corner, which gets neglected in ordinary rules of calculus. In Ito calculus, we will keep that term because of the term db1 and db2. So we know that square of db, right, db square has an order dt, and that is significant, so we cannot drop this term. All right, so the for in stochastic calculus, the expression for d of x1 and x2 is actually given as x1 dx2 plus x2 dx1. This is the common part with ordinary calculus. Then we have sigma 1 sigma 2. As per these two processes, we have sigma 1 sigma 2 times rho dt. Rho dt is coming from db1 times db2. All right, so let's see how that term is coming up. Now db1 and db2 are nothing but two normal distributions, and they are correlated. So we can write db2 in terms of db1 using this decomposition. If you are familiar with Cholesky decomposition, this is precisely what it is. So we write db2 as part of dB2, which is explained by dB1, that is rho dB1, and the other part of dB2, which is idiosyncratic, not explained by dB1. So that is 1 minus rho square square root times dB3. dB3 is some other Brownian motion which is not correlated with dB1. So in this expression, we multiply dB1 on both left hand side and right hand side. Then we take expectation. Now rho times dB1 square is rho dt, because dB1 square is dt. And then expectation of dB3 times dB1 is 0, because they are not correlated. So we get the expectation of dB1 times dB2 as rho dt. What is the variance? Now variance with the same logic can be shown as to be of the order dt square, similar to how we have shown in the case of dB square. This is also product of two dB terms. So the variance of that would be of the order dt square, which we can ignore compared to the expectation, which is rho dt. So essentially, the outcome of this exercise is to understand that dB2 times dB1 will be rho dt. Okay, so that plays a part in the E2 product rule. Now we can cross verify. So if dB1 and dB2 are from the same source, so they are the same randomness, rho would be 1. So in that case, dB1 square would become dt, which we are familiar with. As the last example in this session, we will see the derivation of geometric Brownian motion for stock price process. So we start with this process. ds by s is mu dt plus sigma dB. This is the simple return that we are modeling, which has a mean of mu dt, and the stochastic term is sigma dB. Consider a function f of s as ln s, log of stock price. Then we are going to actually apply Taylor series expansion for change in f. So for that, let's calculate the first order and second order derivatives of f with respect to s. So this is the first order derivative, and this is the second order derivative. Now since our function f of s is a function of s only, so when we apply Taylor series expansion for these type of functions, we are talking about explicit dependence. Does stock price depend on time? Yes. Does stock price depend on Brownian motion? Yes. But the function has explicit dependence on s only. So we'll consider this as univariate function only. So applying Taylor series, we have these two terms, first order term and second order term. And we replace these terms with the derivative calculations that we did. Then we put ds by s as mu dt plus sigma dB from the first equation, and we replace ds with s mu dt plus s sigma dB in the square bracket term, and then we expand that square bracket. Now we look at the terms which we should keep, which are significant in the time interval dt. All right, so we immediately know that dB square is dt, so that we have to keep. The other two terms, one is dt square, which we will ignore, and then the third term is dt times dB, which has an order of dt to the power 3 by 2. That also will get ignored. So collecting the dt terms, we have mu minus half sigma square times dt plus sigma dB. This is the SDE for log of stock price. And why we introduce this variable? Because now it is very easy to integrate. Now all these terms are in differentials. In the first equation had a s in the denominator, which was causing difficulty, but now we can easily integrate. So integrating both sides, we get this. So this, upon simplification, is simply log of st by s0. So st is the terminal stock price, s0 is the starting stock price, is equal to mu minus half sigma square times t plus sigma BT is the Brownian motion at time capital T. We can write it also in this form. St is equal to S0 e to the power the rest of the terms. So this is the famous geometric Brownian motion for stock price, which is used everywhere. It's the most popular model for equity modeling that is used today. So thank you so much. I hope you enjoyed this. See you in the next class.